And this talk is based on the recent work with collaboration with Muxin, and we're finishing the paper. We expect that the paper will be out later this month. So we focus on the loop quantum gravity, or LQG approach to the quantum gravity. And it is a background independent and a non-perturbative approach. And it quantizes the gravity into the building blocks with some microscopic simplices. And one of the promising research areas in LQG is to consider the inclusion of a cosmological constant, lambda. And it's not only to complete the theory, but also it is necessary if you want to apply the quantum gravity to cosmology. And we focus on the covariant approach of the LQG, which is called the spinform. It provides a way to construct the transition amplitude of quantum gravity, so it can be viewed as a regularized path integral or sum over history. We're interested in studying the divergences in the spinform. By construction, it's introduced some fundamental area gaps in the spinform, so it doesn't have ultraviolet divergences, but it does have the infrared divergence when the lambda is taken to be 0. And it's called self-energy or radiative correction in the spinform. Spinform is based on some graphs, which is similar to the Feynman diagram. For a very simple graph, which is just one edge, it's self-energy, first-order self-energy or radiative correction is given by this kind of graph called the Mellon graph. This graph has been studied in one of the most studied spinform model called the e⁻fk model. And this model studies the lambda 0 case. The main idea is to introduce by hand some cutoff for the sum of representations and consider the large cutoff regime of the spinform model. And the recent study for this radiative correction for the Mellon graph find that the amplitude scales linearly in this cutoff. This result is also consistent with the earlier result of the lower and upper bound for these amplitudes. Now we want to study it from a different starting point, which is to start from a spinform model with really a non-zero cosmological constant. And our project is based on the spinform model constructed 2 years ago, which is a spinform model based on the SL2C Chern-Simons theory on the boundary of a four manifold. And the benefits of this manifold are mainly in twofolds. Firstly, this amplitude, it provides an amplitude that is finite by construction. Its cutoff is provided by the cosmological constant in this relation. And secondly, it provides a correct semi-classical limit, which is the four-dimensional radial calculus with either positive or negative cosmological constant. So we did it analytically and find that the radiative correction follows the power law. The amplitude for the Mellon graph has a power in K, and I will explain what its power is in this talk. So I will first give a very quick review on this spinform model, and then consider the spinform amplitude for the Mellon graph, and later the radiative correction corresponding to this Mellon graph. So very quickly, spinform model is based on a so-called local amplitude ansatz on a given spinform 2 complex. A spinform 2 complex is a dual graph to a triangulation of four manifold as described in this table. So it associates, the amplitude is given by packages of amplitudes on local simplices. It associates a phase amplitude for each triangle, an edge amplitude to each tetrahedron, and a vertex amplitude to each four simplex. And this graph is a graph that is dual to a four simplex. And in particular, the phase amplitude is the standard way is to choose it to be the dimension of the representation to some power. And the vertex amplitude encodes the local loop quantum gravity dynamics. The goal of the spinform program is to construct these amplitudes that is consistent and suitable, so that and they can implement the quantum dynamics of loop quantum gravity. And the main part is to construct the vertex amplitude. The starting point to build this spinform model is to start from the Plabansky formalism of 4D gravity. It formulates gravity into a BF theory with some simplicity constraints. And the action, when we add the cosmological constant, it has a quadratic term in the B field. And the simplicity constraint relates the B field to the tetra field. There are mainly two steps in the spinform model. First is to construct the path integral. In this action, when we integrate out the B field, we need to do a Gaussian integral, which gives us a constraint that relates the curvature to the B field. Then with the path integral can be written in terms of a 4D topological term, which can be written as a Chern-Simons theory on the boundary with complex coupling constant. This gives the partition function of the Chern-Simons theory, and the main second step is to quantize the simplicity constraints and impose them quantumly. And it turns out that the 4D quantum gravity with a non-zero cosmological constant can be understood as a complex Chern-Simons theory on the graph complement of the boundary with simplicity constraints that is imposed on the graph. This graph is called the gamma phi graph in this way. And the graph complement is the gamma phi graph complement of a 3-sphere. The partition function has been shown in the original work that it can be written as a finite sum and convergence state integral, so it's finite. This is the explicit form of this partition function. And here the phi delta is called the quantum dilogarithm function. And this is because the building block of the triangulation of this 3 manifold is given by the ideal tetrahedron, which is a tetrahedron with all the vertices truncated. And the second step is to impose the simplicity constraint, and it leads to the definition of the vertex amplitude. And it's defined as the inner product of this partition function with 5 coordinate states, each on one vertex of the graph. So that is the vertex amplitude. Now I want to also write the spinform amplitude for the Mellon graph. The Mellon graph is considered 2 copies of these 3 manifolds, and then glue 4 of the 4-hole sphere out of 5 4-hole sphere in these 3 manifolds. To glue them, we can write out the gluing constraints, which can geometrically understood as matching the geometry of this triangulation of the 4-hole sphere. The triangulation of 4-hole sphere are the curved tetrahedron, either spherical or hyperbolic, depending on the sign of the cosmological constant. And then we can impose the simplicity constraint, which can be obtained by factorize this amplitude into 2 vertex amplitudes and 4 edge amplitudes. Graphically, it can be understood. Can be understood as changing, splitting this graph into 2 copies and include with some edge amplitudes. To do this, technically, we use the over-completeness of the coordinate state and change delta in terms of the inner product of the coordinate states. And so now we can derive an edge amplitude that is consistent with the vertex amplitudes. As a last piece, because now we also, in this graph, we also have some internal phases, so we also need to add some phase amplitudes to the total amplitude. And in the end, we wrote the amplitudes for this manifold that emits the local amplitude ansatz. And we proved that this amplitude is finite. For this amplitude, we are interested in the regime where the k goes to, the cutoff goes to infinity, or effectively, the cosmological constant value goes to 0. The main techniques to do this are first to use the Poisson summation to change the summation to integral, and secondly, we change the coordinates to those that doesn't scale with the k. Then we can write this amplitude at the large k regime in terms of some effective action. And graphically, this at the large k regime, you can understand that all the boundary data are not seen. at this regime. So the result is the following. The effective action are some polynomials in terms of the scaleless coordinates and coordinate state labels, and some logarithm function in terms of the coordinates. And importantly, this effective action at the stationary point doesn't scale with a k. So the scaling are only in the prefactor and the determinant of the Hessian, which turns out to be polynomials in k. Then the scaling of this Mellon graph, the amplitude of the Mellon graph is just comes from just power counting. It scales as k to the 12 plus 6 mu power, where mu comes from the phase amplitude. So this would diverge when the mu is larger than -2. This result does depends on a technical assumption that the Hessian is not degenerate. We did some numerical experiments to check that it can be the case, but strictly speaking, if we encounter some space-time point, some phase-space point where this Hessian is degenerate, then the power will increase. So this is a lower bound for the divergence. Let me conclude. In this work, we considered the Mellonic radiative correction for the spinform with a non-zero cosmological constant. And it scales as 1 over the cosmological constant to the 12 plus 6 mu power given this phase amplitude. This result is promising because we really start from a spinform model with a non-zero cosmological constant. In the scheme of this work, we also propose an edge amplitude that is consistent with the vertex amplitude. And it's as the first application of this spinform model, we find that this spinform model is as computable as the e power fk model. So for the future, we expect we can improve the analysis for the Hessian by using some numerical method that's used for the e power fk. And we also it's also interested to see the connection with the e power fk model. And the main thing is to find the relation of the coordinate states used in this model, spinform and e power fk model. And it's also interesting to see the relation of the spinform and the canonical quantization of for the gravity, which related to the combinatorial quantization, and it might lead us to see if there is some emergence of quantum groups. Thank you.
Thank you, Qiaoyin, for the nice talk. I see one question by Bianca.
EPL if you send lambda to 0?
Yeah, thanks for the question. So in this construction, there are mainly two differences. First, we introduce the edge amplitude that's very different from EPRL. And secondly, the coherent state we define here is based on the Chern-Simons theory. So I call it Chern-Simons coherent state. So the coherent state is also different. So to really see the connection, or if it's really match the results in the EPRL model, then we should study in detail what's the relation between the coherent states. Yeah.
Sebastian?
So then does the difference to the EPL model come from this different edge amplitude? Because that comes with the scaling as well, typically.
Yes. So in the EPRL FK model, the edge amplitude is just the delta function. But in this model, so it doesn't give the scale of in the K. But in this model, we choose the coherent state to build up the edge amplitude. It actually scales as totally K to the 12. So yeah.
One last question, and then.
This mu is a free parameter, is it?
Mu?
That mu parameter, is it free, or
Mu, it needs to be fixed. So we choose one mu.
yeah, then you can, if you take mu sufficiently negative, you will get a finite spinform model.
That is true. So up to the
So
choice.
what's the problem? You know, I don't see.
What is the problem?
Yeah.
So as in the EPRL model, the lambda 0 case, so the mu is chosen to be 1. So in the at least in the lambda 0 case, we expect the spinform amplitude to diverge. So so if we choose mu to be very small, then so that the amplitude doesn't diverge, then there's a gap to relate this result to the lambda 0 spinform model.
For lambda equals 0, I did some work with Marco some years ago. Even for lambda equals 0, if you use this thing of dividing by a sufficient power of dimensions of j, you can get a finite amplitude. No divergence.
Okay, I think we should stop now and maybe continue the discussions later.
Okay.
Thank you, Qiaoyin, again, for the nice talk. Can you, you can switch the mic. Our next speaker is